Okay, so we have another definite integral here. We're going to sketch the region represented by this integral and evaluate this integral. Okay, so here we have a sine function, y equals sine of x, and hopefully that's not too much of a stretch to think about what that graph looks like. So sine wave, you know what a sine wave looks like. Maximum value of 1, minimum value of -1, period of 2 pi. All right, so we are interested in the signed area between that function and the x-axis on the interval 0 to pi. So our interval, x equals 0, is right here, and x equals pi is going to be right there. The period of that sine wave is 2 pi, so halfway through we would be here at pi. So here's our interval, 0 to pi. And so we have a signed area, in this case true area, because that function is always above the x-axis on that region, from x equals 0 to pi. So we've sketched the region represented by that integral. It's this region right here. And now we want to evaluate that integral. So we looked at some integrals where we had an area formula from basic geometry. We looked at some circles, or in your homework you have rectangles, triangles, some regions where you know a basic area formula, and you can just find the area or signed area of that region using basic geometry. But this, although it may look sort of like a circle, is not actually a circle on that region. So this is not the equation of a circle. So we need to use something else here to find the value of this integral, which will represent this area that we have right here. All right, so the most important theorem in all of calculus. It sounds like the most important theorem in all of calculus because it has a very important sounding name, the fundamental theorem of calculus. One of the parts of the fundamental theorem of calculus says that if your function is continuous on your interval, this function is continuous everywhere, so certainly on the interval 0 to pi, and if you have an antiderivative of this function, then you can use that to evaluate this integral and find the area of this region. Okay, so in the statement of the fundamental theorem of calculus, it talks about little f of x as the function being continuous on the interval. And so we said this function is continuous everywhere, so certainly on that interval from 0 to pi. And I need capital F of x, which is an antiderivative of that little f of x. So capital F of x, which is an indefinite integral, an antiderivative of this function. Okay, so this should be one that you know. We also know that if we have an antiderivative that I need to find that is not one I know, we have a technique called U substitution that we might be able to use. But this is one you know. So you should know that the derivative of cosine is negative sine. So the antiderivative of sine is negative cosine of x plus c, if we're talking about antiderivatives. All right, so the fundamental theorem of calculus says that if your function, y equals sine of x, is continuous on your interval, a to b, and you have an antiderivative of that function on that interval, then you can use that to evaluate the integral. So we'll write that out over here. All right, so using the fundamental theorem of calculus, my integral from 0 to pi of sine of x dx is going to be equal to any antiderivative. I'm going to use c equals 0, just because that's a little bit easier to use here. Any antiderivative of this function, so negative cosine of x plus any c you want, I used c equals 0, evaluated from 0 to pi. So here I have a definite integral. Fundamental theorem of calculus is what connects that to antiderivatives. Here's my antiderivative, evaluated from 0 to pi. And then in the statement of fundamental theorem of calculus, it says that this is going to be equal to capital F of b, or b is pi, minus capital F of 0, a. Right, so I need to evaluate this function from 0 to pi. I'm going to plug in the 0 first. I'm going to plug in the pi first. negative cosine of pi minus negative cosine of 0. All right, so I've written down the antiderivative. This symbol means evaluated from 0 to pi. I need to make sure I evaluate them in the correct order. It's the upper limit of integration plugged in first, minus the function evaluated at the lower limit of integration. And then these are both values you know. You know that cosine of pi is negative 1. I'm going to simplify this minus a negative that I have right here and just make that plus. And then cosine of 0 is 1. So I have negative of negative 1, which is 1, plus 1 equals 2. Okay, so this integral is 2. That is the area of this region. And we did it this time using the fundamental theorem of calculus, right? Fundamental theorem of calculus, big important theorem. That's the big deal thing to learn from Calc 1. Antiderivative, evaluated in this correct order, connects derivatives to areas of regions. All right, we'll look at some more examples.